G'day, welcome to, I think it's the 10th video now on integration. Now this particular video we're looking at approximate areas, 7.6 in your textbook. This is kind of the origins behind integration, which is kind of looking at the area underneath a curve between 2 points. And this is kind of where we start with the whole thing. So this is not a precise way of doing it, this is an approximation way, but it is on the syllabus, so we do need to learn how to do this. So the first method I want to show you is the left rectangle method. So this method involves breaking up the area bounded by the curve and the x-axis into rectangles, with the left-hand side of the rectangle touching the curve. What do I mean by that? Let's have a look at this example just here. So I've got a curve which is x squared plus 1, some rule, and I'm going to break up the area between, say, when x is 1 and x is 4. I'm going to break that up into 4 rectangles, and the way that I'm going to break that up is I'm going to have the top left-hand part of the rectangle is touching the curve, and then it goes straight across from there and down. Okay, so touches the curve, straight across, down. Touches the curve, straight across, down. Touches the curve, straight across, down. Okay, that's how we're going to work out using the left-hand rectangle method. The left-hand side is going to be touching the curve in order to approximate the area underneath this curve. And then what we need to do in order to work out the area of a rectangle, it's just simply the base times the height. The base times the height. So this one, the area of the first rectangle is going to be base times the height. The second one, base times this height, base times this height, base times this height. Now the height of each one is actually what the y value is at that given x value. So for example, the first one, when x is 0, I'm going to go up and I'm going to find the curve that when x is 0, I'm going to get a y value, and that's the height of this first rectangle. When x is 1, that will be the height of the next rectangle. When x is 2, I'll get the height of the next rectangle. When x is 3, I'll get the height of the next rectangle. Okay, and it's all, the bases are all 1, so that makes it fairly straightforward. So the total area of the of this underneath the curve, an approximation obviously, is the base times all of the heights together added up, which ends up being 1 multiplied by f of 0 plus f of 1 plus f of 2 plus f of 3. And I can actually find out what those are. I sub in x equals 0 into this equation, and I end up getting the answers of 1, 2, 5 and 10. And I do 1 multiplied by all of those things added up together, which ends up being 18 square units. So this is an approximation. It's not exact, but it's not too bad. It does depend, let me show you the areas that are not included, as you can probably already tell, but all of the red bits are the bits that are included, and all of the blue bits are the bits that aren't included. Okay, so those are the bits that I've missed out. The smaller you make the base, the more accurate your answer is going to be. Let me show you an example of 2 that I've got here. If I make a rectangle with width of 2, as you can see, the first one here, that first rectangle is actually not existent because I have to start at the y. Have to start where the graph is on the left-hand side, and then the second rectangle will be here, and that'll give me a lot. But there's a lot in here that I'm missing. But if I have a rectangle with width 1, same function, I can actually break that up into 4 smaller rectangles, and as you can see, there's far less that I'm actually missing out. And if I made the rectangles a half, you'd actually get closer to it. And the smaller you make the rectangle, the more accurate it's going to be. And in fact, when we do the proper integration, we'll actually make, I guess essentially we're making the rectangles almost nothing, like the width almost nothing, so that we can actually find out what the exact area is. And that's kind of the theory behind all of this. So let me now show you the right rectangle method. It's exactly the same theory. Instead of starting from the left, we start from the right. That's really the only difference. Okay. So it involves breaking up the area bounded by the curve and the x-axis into rectangles, with the right side of the rectangle touching the curve. So for example, I'll use the same shape that we had before. Instead of starting at the y-axis here, I'm going to start at when x is 1, and I'm going to start there and move backwards to make the rectangle. Okay, and then I start at x is 2 and I move backwards to make the rectangle. When x is 3, move backwards to make the next rectangle. It's tricky to say. And then when x is 4, and then work backwards to find the next rectangle. Okay, so it's the same idea, same rectangles. The only difference is that now I've actually got an over approximation, whereas before I had an under approximation. And that depends on the type of graph that you got as well. So if I look at the bases are all 1. But if I look at the heights, the heights are actually, I've still got F1, F2 and F3 there, but I don't have F0 because that's if I was taking from the left hand side. I've actually got F1, F2, F3, F4. So generally speaking, the left-hand rectangle method will start from the lowest one and go up to one less than the highest one. And the right-hand rectangle method will start actually almost from the second part and go right up until the end. I hope that makes a little bit of sense. You might actually start to see this when you're doing some questions. Okay, so I'll just continue back along with this one. So I get... For this one, I get my base times all of the heights together, and all of the heights just end up being F1, F2, F3, F4, and I've already worked out some of those already, but it ends up being this 2 plus 5 plus 10 plus 17, which ends up being 34 square units. Now, as you can see, this is an over approximation because there's bits that I've actually included that aren't under the curve, and if I compare the two, the left-hand rectangle method was 18 square units, the right-hand rectangle method was 34 square units. So generally speaking, if I have I've got two types of functions, an increasing function and a decreasing function. An increasing function is, I guess, there's some more technical definitions which I'll go through a little bit later, but it looks like it's sort of doing this. It's like increasing, the next y value is higher than the previous y value. And a decreasing function is doing the opposite. The next y value is smaller than the previous y value. There are more definitions than that, but let's just go with this. Now, if you're using the left-hand rectangle method, then you'll actually get rectangles that look like this. So you'll get an under approximation. And if you've got the right-hand rectangle method on this, maybe I'll do it in a slightly different color, you'll get the similar types of rectangles, but they will actually be an over approximation here, like this. So the right-hand rectangle method is going to be this one, the left-hand rectangle method is going to be this one. So for an increasing function, and I guess I've got the technical definitions over here, that the f of b is greater than f of a, so the next y value is greater than the previous y value when b is bigger than a. That means that your right-hand method is going to be an over approximation, bigger than the actual area, and the left-hand rectangle method is going to be less than the actual area. And it's the opposite for a decreasing function. The left-hand rectangle method, I'll do that in red, that's actually going to be the over approximation here. Okay, like that. And the blue is going to be an under approximation because I'm going to use this part. Ooh, let me get blue. I'm going to use this part here, this part here, this part here. Okay, so it's kind of the opposite. Hopefully that makes a little bit of sense. I can explain that more in class. It's just helpful to know that one will be an over approximation, one will be an under approximation as well. Now, it's not like these ways of working these graphs out. It's not limited to rectangles. You could actually use any shape. In fact, I've seen other times we've used trapeziums to work out that. In fact, sometimes we've worked out the area not from the left or the right, but from actually the middle of the graph. All of these things I might just touch up in class. They're not a big part of the course. In fact, I haven't seen many questions on them, but you do need to be sort of prepared for anything. It's the same theory, you've just got to adapt it slightly. So that's the approximation videos, and in the next video we'll look at how to get the actual area for all of the areas under the curve. So thanks for watching.